Hi everyone. Welcome to this webinar on machine learning and mean-field games. The first one for this academic year. And today we're very happy to have Patrick Benjamin from Oxford University. So Patrick is a student at Oxford University of Oxford with Alessandro Abate. And so today Patrick is going to present his work related to mean-field games and network communication for decentralized agents. So thank you very much, Patrick, for accepting the invitation. And
Thank you very much.
please take it from here. Thanks.
Yes. Very nice to have the opportunity to speak to you all. There's certainly some names I recognize in the list here. And yeah, as Mathieu says, I'm just coming to the end of the first proper year of my PhD, which means that I'm certainly aware of having less experience in some of these things than the people that I'm talking to on this call. So I'm very much looking forward to getting some feedback and having some good interaction with people. So please feel free to interrupt me during if there's anything that needs clarifying or any questions. Otherwise, happy to take questions at the end, of course. Okay, right, already I can't change the slide. Right, here we go. So the broad kind of outline of what I'm going to cover, just so you can try and keep track of where we are. I'll introduce, I imagine a lot of you are familiar with mean-field games, but I'll give a brief kind of motivation for that, and also my proposal of this networked setting. I'll give you some of the kind of the more formal background to that so that we can make sense of things, talk about the algorithm that I'll be focusing on in particular, talking about some of the benefits to do with robustness that I think my contribution can bring, and then start explaining some of the current and future work that I'm looking at in this area, which, as I emphasize, is very much ongoing, and I think that'll be a running theme on some of the slides of this. I should emphasize this is not finalized work, but hopefully there's things it's interesting to me. Hopefully, it will also be interesting to you in terms of things to think about in how we can bring communication into these algorithms. So first of all, mean-field games. Again, I won't dwell too much on it because I imagine that if you're here, you share my view that they are interesting and important. But essentially, if we think of multi-agent reinforcement learning and also multi-agent systems more generally as being quite difficult to scale as you increase the number of agents, that means that each player of the game has to the joint state and action space increases exponentially as you add more agents, which gives a kind of a computational bottleneck for reasoning about how to play these games. And yet there's every reason to believe that very large populations of agents are kind of more realistic in the real world and also potentially more useful. So lots of work on multi-agent RL can only really handle a handful of agents, when in reality with cities full of autonomous cars or drones or sensor systems or satellites, we might be thinking more in the region of hundreds or thousands or even millions of agents. So in order to tackle that scalability obstacle, we can use the mean-field game framework to approximate solutions. The mean-field game framework relies on an infinite population, but we can use that to approximate solutions for large finite populations. And at heart, the idea is that each agent doesn't consider itself as playing against each other opponent individually, but against the distribution of what all of its opponents are doing. So it kind of almost collapses back into to being a two-player game, which is easier to reason about. And I'm not gonna explain too much about the network communication here before I go into some of the background, because it's going to make more sense after some of the preliminaries. But just to say at a high level, the motivation is that a lot of the existing algorithms, again, I'm sure many of you are familiar with them and are likely to have worked on them yourselves, rely on certain assumptions about how the algorithm can manipulate this mean field distribution, which may not actually be desirable assumptions for these complex real world problems involving cars or robots and so on. So when applicable, my argument is that communicating between agents can actually help to overcome some of these unrealistic or undesirable assumptions and bring certain benefits while doing so. But as I say, this is the idea is one that I believe in, and I've got some preliminary results, but definitely, as you will see, some of my hypotheses are yet to kind of really be demonstrated or proven beyond reasonable doubt. So yeah, lots of future work to be done here. So just to tackle some of the kind of the preliminaries, this is more of a notation slide. The main thing to really worry about here is, I don't know if you can you see my cursor moving when I point? Okay, good.
Yeah.
This is the idea of the empirical state distribution, so the mean field, but which is often in the literature characterized by this mu, which is a distribution over the states, but specifically here, I will be thinking about an empirical distribution. So that is worth remembering, this mu hat. And then as in lots of reinforcement learning settings, we have policies that map states to action distributions, and we have Q functions that evaluate how good our taking actions in certain states are. So firstly, we can think about, because ultimately what we are using these, I mean, or at least from kind of my view of these things is that I know other people are looking at mean field games from a more kind of pure theoretical perspective. From my point of view, I'm interested in them as an approximation for this n player game. So if we can think of the n player game to start with as involving symmetric and anonymous agents, what that really means or refers to is these two terms here at the bottom, which are basically saying that the transition function and the reward function are symmetrical, identical for each agent, and also, rather than as in a kind of conventional multi-agent RL setting, being reliant on the action taken by each other agent individually, kind of indexed by the agent, we instead look at this empirical distribution of what everyone else is doing. So hopefully that's reasonably clear so far. We have this notion of the n player discounted and regularized reward. We can, I know you've had previous discussions on in seminars about whether or not you need the regularization. Some of the work that I'm basing my own algorithms on, it builds off some of the algorithms that were discussed in Niao He's talk a few months ago. So if any of you remember that there'll be some crossover there. So the idea is that an agent I has this expected discounted regularized reward, where H is this regularization function. Now, the reason that this is important is to consider the Nash equilibrium of this game, and in particular, we can think of a delta Nash equilibrium, which is basically to say that no agent can benefit by more than delta by deviating from the current policy, the tuple of policies that everyone is following.
Patrick, can I ask a quick question? Sorry for the interruption.
Not at all.
So here you look at policies. So the board pi is a vector of policies for all the players.
Yeah.
And you are looking at stationary policies or potentially
so in my work so far, I'm thinking of stationary mean field games. I haven't made that explicit.
Okay.
So currently, well, the learning process, the policies obviously evolve towards the equilibrium, but the policy is a stationary policy. As part of future work, I'll mention in kind of one of the last slides, I'm hoping to move on to these non-stationary policies. But yeah, for now, this is each agent can have its own policy, but that's what the tuple.
Okay, thanks.
Okay, good. Now, as I said, solving the n player game is very difficult, as I'm sure you all know, but we can instead approximate a solution to that n player game as n tends to infinity. We can think instead about the mean field game with the limit distribution instead of an empirical distribution of the agents. And here instead we have V instead of J. This is not indexed because obviously you've got an infinite population rather than a finite population. And here the idea is that for the distribution, for the mean field arising from everyone following a certain policy, this is the equivalent of the discounted regularized reward. Again, as in the n player case, that discounted regularized reward is important for allowing us to think about the Nash equilibrium. So in a very kind of abstract sense, the Nash equilibrium of this, stationary mean field game here is this kind of forward backward set of equations, coupled equations, where we have the pair pi star and mu star. Pi star is the best possible response to the current distribution, and that distribution is itself the mean field that arises when everyone is following that pi star. And crucially, other people have shown that the mean field solution is kind of this delta Nash equilibrium of the n player game. So as I'm sure many of you are aware, kind of early and kind of more conventional methods for looking at trying to find these mean field or the Nash equilibrium to the mean field games essentially involve a variety of methods for solving this coupled system of equations. I can't remember what's on my next slide. So, okay. The coupled system of equations, and certainly in a lot of the existing literature, there is this idea of having a centralized controller that is learning a policy in response to this distribution and updating the distribution with a new policy and kind of iterating these two forward and backwards equations towards the solution. And the reason we have that regularization term that I mentioned earlier is to allow that to be contractive. But yeah, so a lot of algorithms think about the policy and the distribution evolving maybe at different time scales, and crucially, the algorithm kind of has an access, an ability to both sample kind of arbitrarily from that distribution and also manipulate it in a way that, as I will elaborate on in a second, may not actually be realistic for real world problems. Just to clarify, because it's going to be important later, this idea of exploitability, again, I'm sure many of you are aware, this is the metric that normally we're most interested in when thinking about how close we are to converging to the Nash equilibrium. The idea is essentially, it's that how much can you benefit, how much can an optimally playing player benefit by deviating from the current policy. So when you're at the Nash equilibrium, you shouldn't be able to benefit at all by deviating, so exploitability should be close to zero, whereas at the beginning of the learning process, you might expect it to be a lot higher, and then you should be kind of decreasing if everything is going well. But I should note that, again, because, as I say, a lot of traditional methods focus on this centralized setting. Normally, in the centralized setting, you're only really thinking about this because everyone's following the same policy. You don't have to factor in the fact of in settings where each agent is actually learning independently, as I'll mention in a second. then you've actually got the exploitability of the joint, the tuple of policies where everyone is doing something slightly different, which is not quite the same thing as, so that you have to think about the tuple rather than the exploitability of the individual policy. So having gone over all of those preliminaries, I think we're now kind of in a better position to talk about why network communication might be better. So, or not necessarily better, but might be beneficial. So as I've mentioned, a lot of algorithms are mainly focusing on those equations, solving them analytically, or as I say, using oracles to sample from or directly manipulate that distribution. But when you've got, for example, a city of autonomous cars or a complex system of robots or drones, you can't necessarily expect to arbitrarily switch around the car's positions. To give a very kind of intuitive example, and actually you just need to learn from the continued evolution of the systems. In other words, you might expect your algorithm to have access to the policy of the agents, but not necessarily have access to manipulating the mean field. So some more recent work has instead focused on learn, and this is the work I was referring to that Niall He spoke about a few months ago, which I have a citation for in a slide or two. Think about learning from this continued task rather than a continued task with this empirical n agent population, rather than doing things on different timescales and so on. So crucially, we're interested in the n agent population. We're trying to solve that with the infinite, using the infinite population as an approximation. But now I'm saying, actually, you can't necessarily assume that you can manipulate this infinite population. So you do have to, again, kind of almost approximate your infinite population with your empirical n agent population. So that's you're kind of going back and forth between the two slightly. So in these settings where you're just learning from a continued trajectory or evolution of your system, and it's still, even if it's not an infinite population, it's still a very large finite population, having a central controller is quite a strong assumption. Again, if we're thinking in terms of a city of cars, you're unlikely to, or it may be undesirable to have one single learner that is orchestrating the learning process on behalf of all of the thousands of agents that are learning, both in terms of the kind of the computational and communication scalability, but also if that one central learner were to fail or go down for some reason, then the whole system breaks, which obviously for important real world systems is undesirable. So here is the citation that I was mentioning. Some more recent work, and not just this one, but this is the kind of the one that is most similar to my own work, have thought about, rather than learning with a centralized learner, having each of the n agents trying to solve this problem independently. The problem being that the independent learning case, where each agent is learning by itself, they prove in this paper has much worse sample guarantees than the centralized case, for reasons that I'm going to come back to a bit later. So now for the core kind of crux of my argument, is that if on the one hand we have the centralized case, and on the other hand we have the independent case, kind of a middle ground is this inter-agent communication case that I'm presenting. And my argument is that it helps to remove some of the kind of the unrealistic assumption of a centralized controller, and some of the potential pitfalls of that, while also bringing hopefully benefits over the independent case in certain ways. So for in order to talk about this network case, I'm not going to dwell on this notation too much, but we can think of it ourselves as having this time-varying communication network. So the agents can communicate within a certain kind of radius, again, I should emphasize also that I'm talking about agents that are mobile and move around, but a lot of this stuff is also applicable to agents that are like in a sensor network, are fixed in place, but the same arguments apply. But nevertheless, the network might be varying as agents move around or have different signal strengths. So they'll be able to communicate with different numbers or areas of their neighbors as the learning process goes on. So those are the preliminaries. I realize there's a lot of letters and numbers on this slide. The key thing to remember, or the key thing to kind of to gain from this slide, and this is based on the work that I've been mentioning before, their kind of learning algorithm for this continued system evolution. The point to get from this slide is that you have a learning update where the agents, be it a centralized agent or the independent learning agents, are going around collecting transitions, and then once they've got some of those transitions, they update their estimation of the Q function, which is estimating the value of the value of the current policy with respect to the current mean field. So that's what this is doing. We have a Q function kind of learner, and then having learned that Q function, we then update our policy by performing this. There's a question.
Sorry, I think there is a question.
Yeah. Yeah, please.
Hey, sorry, just because I got lost in the lots of symbols. You have a gamma there that it is an extra learning rate, or did I missed something?
The gamma, this is not the learning rate. This is the discounting factor.
The discount. Okay, sorry, I just lost it from the previous definition.
No. So the beta is the learning rate. The gamma is your normal discount factor that you have in reinforcement learning.
Okay, thank you.
That's all right.
Yeah,
I mean
yeah, sure. Oh yeah, sorry, go ahead.
No, after you.
Just one follow-up question on this equation. So is it correct to say that each agent, so agent I has, I mean, they have their own QI. Somehow each agent has a Q function, and they update using their own observation. So they do like kind of independent updates. For now, the updates are independent on this equation.
Yeah.
Okay.
Yeah. So I'm just going to introduce the policy. I'll clarify that in one slide.
Thanks.
So you have the policy update operator. So having either the centralized learner or, as you say, the independent learners, they take this learnt or estimated Q function, and then they take a step to improve it. And the way they do that, according to this current algorithm, is that they use the current Q function, which, as you say, in the independent learning case, would be indexed by the one that they have individually learnt. And they're maximizing a combination of these three terms here. So the first one is they're maximizing the kind of the action distribution with respect to this estimated Q function. They're also maximizing this regularizer term, which in my experiments, and I'm sure is probably most obvious to a lot of people, to think about the entropy regularizer. And then we're also, this final term is essentially the learning rate that controls how big a step we make in improving our policy. It's this term is a similarity term between the new policy and the existing one. So by changing this eta here, we can vary how big a step we're taking. So again, the key takeaways here are: we estimate a Q function, we update the policy. And now, again, big algorithm and confusing. I'm aware of that. We can talk about the details more, but I just wanted to show it while again giving a kind of a visual instinct to the high level important bits. This is where we're having this loop where agents are collecting samples and moving around. They're performing this Q function. estimation procedure. Once they've done that for a while, they update their policy. So ignoring the blue bit, sorry, I'm covering it with my hand as if you can all see where my hand's going, which obviously you can't. Ignoring the blue bit, we have the existing policy in the paper by Niauhe and others, which here, yes, is the independent learning case. So there's a queue, there's an I for each, there is a queue for each agent, and each agent is learning an independent policy based on their independently estimated queue function. But the way they do it in the centralized case is that agent with index 1 is the only one that's doing this learning, and then it pushes out the policy, the learned updated policy at each iteration to all of the other agents. So that's how the centralized learner works. It's just one agent that is sharing its update with everyone. So my contribution, and again, I will come back to this in a bit more detail, but don't want to go too much into it now, is this communication section where agents, having updated their policy, they assign a value to it. So I'm assuming to start with that we want to get as close as possible to the centralized case, but doing it in a decentralized way. The centralized case being where there is a single policy after the policy updates, but I'm achieving that by having a certain number of communication rounds between the agents and their neighbors. Obviously, to converge on a consensus policy, we need a mechanism for making sure the agents are all choosing the same policy. So we assign to the agents a way of assigning a value. Sorry, we give the agents a way of assigning a value to their policy, and then they're essentially taking the minimum value. So if we think about networks in general, if other works have shown that if agents always choosing the minimum value of a value received from their neighbors, eventually they will converge on the same minimum value. So what I'm doing here is by assigning each policy a unique value, we should also converge on a unique policy by the end as well. I'm going to talk more about how we decide that value in a second, but just to start with, the idea is that you're hopefully going to have enough communication rounds to end up with a unique policy at the end. So this is the kind of the simplest case and the one I'll start with, and then I start to murky the waters a bit after that. So I'll introduce the concept of some of these concerns around robustness first and how I can tackle that. Robustness has not massively been thought about so far in mean field games, or at least not in the senses that I am thinking about them. The reason for that being that obviously a lot of the work has been pretty theoretical and thinking more about finding converging to the solution rather than how it might be deployed in the real world. But when you are thinking about the real world, you're likely to come up against problems such as agents, especially if they're decentralized, failing to be able to take their update step. A particular reason that might happen is because, as you can see, this is currently a very involved algorithm with lots of nested loops. And if we're having decentralized agents trying to do all these nested loops together, then there's some susceptibility to kind of synchrony failures, which might mean that we need an internal kind of clock tick to make sure agents are learning, which might mean that someone doesn't manage to update their policy before the clock tick happens. So you might have failed to, in the decentralized case, you might have failed to update. And equally, we can think about it might be important to be able to handle changes in the size of the population. Obviously, most mean field work so far think purely about just an infinite population, but actually in reality, you might have extra fleets of autonomous cars joining or additional numbers of drones joining, and we need to be able to think about whether that affects our learning process or our equilibrium. So here's some kind of preliminary results on some very simple tasks, just to illustrate how the networking case gets around that. This is a target coverage task. The agents are told that they kind of, it's a bit like a congestion game. They need to cover the four corners, but do so in a way that's as evenly spread between them as possible. And the point I'm making here is that in the centralized case, if there's a 50% chance of failing to update at each iteration, then, as I said before, that is a single point of failure. So it just doesn't update at all. And the same with a decentralized or an completely independent learner. If it doesn't update, it doesn't update. But the benefit of a networked system is that the kind of the knowledge that is gained is held within the network as a whole, rather than any one agent or any one central controller. So they can spread, the agents that have managed to update can propagate their learned policies to the ones around them that have not managed to update. So we can see, kind of in simple terms, this is the this is the kind of the reward in going up, and this is the exploitability. This is the difference between the different policies. So you can see that in the independent case, the policies end up diverging, as you might expect, given that they're all learning separately. But in the centralized and network cases, there's not much policy divergence. This is the same on another game, where instead of spreading out between the four corners, we have a grid, and agents have to choose which of the four corners to coordinate on gathering at. Again, similar thing. You can see that networked learning allows the process of learning to continue, even when in the centralized and independent cases, they are going much slower. Now, in the case of the sudden increases in population, my argument is that if we're expecting all the newly added agents, the new fleets of drones or cars, if we're expecting them to kind of catch up with the rest of the population in a purely independent way, obviously you're going to have a big gain in exploitability, and that could potentially throw off the whole equilibrium. Whereas in the network case, again, you can very quickly spread your knowledge through the population while also not relying on the centralized controller. And then this is a very messy graph that is trying to show the same thing for the other task, the target selection task. So there's something to be said, it seems, for the networked case, this networked addition for robustness. But obviously, as I mentioned before, one of the kind of equally important things is speed of convergence. And ultimately, I would like to be able to solve the problem that we see of independent learning having, at least theoretically, much worse sample guarantees than the centralized learning case. So I'd like to be able to tackle that with the networked algorithm, and we'll see how successful or not I have been with that in the next few slides. So again, there's a lot of text here. The point that I'm really trying to get across is, unsurprisingly, the highlighted bit. What this is saying is the reason we have the difference in sample guarantee between the centralized case and in the independent learning case is that because the independent learners are independently updating their policies due to the stochasticity of the update, there ends up being divergence. They're not all, they're not all having an identical policy pushed out to them, which gives error to the TD update, the Q function learning bit, because as you're aware, the mean field game framework is assuming that everyone is following the same policy. And if they're not actually following the same policy, which is this delta, this is the divergence between the average divergence between all the agent's policies, that adds bias to the Q function update. And then because there's this bias, we need to run a lot more iterations of the algorithm in order to converge. So it seems that lowering the amount of policy divergence would be a good way of potentially improving our sample guarantees.
So going back,
Yeah,
Quick
of
question,
course.
Patrick. On
Yeah,
this result, so in the left, you have Q hat M, which is after M iterations, I guess, M loops.
yeah.
I don't see M in the right-hand side, so does it mean that, even if you do infinitely many updates, this kind of upper bound is not improving?
Yeah, no, you have, as it says that there's this non-vanishing bias,
Yeah,
basically.
yeah. Okay.
Um,
So it doesn't necessarily, okay, maybe we don't, I don't know. I don't know if it's known whether it's a tight upper bound or not. Maybe it's not tight, but at least the upper bound is not improving. It could be that
um,
actually it's going to zero, but the upper bound is not showing that, right? That's what you mean.
yeah, I think the idea is that if because you've also got another loop that is updating the policies, if the policies are converging such that the divergence
Okay,
is going down, then also this error will also go down.
I see.
But it wouldn't go down unless the policy
Yeah.
divergence is increasing.
Okay, thanks a lot. Yeah.
Okay, so going back to the details that we weren't looking at before in my communication algorithm. So to start with, the way I assigned that unique value to each policy that allows a consensus to be reached was by trying to minimize the difference between the existing policy and the previous policy. So there were two reasons for this. Well, three. One, if you assume that consensus is reached arbitrarily, it almost, as in regardless of the value, it almost doesn't matter how you find that value, but obviously we can do better than just assigning an arbitrary value to each policy. Secondly, given that this is we're essentially minimizing the distance, that's like minimizing that learning rate that we saw earlier in the policy update. So it seems to give quite smooth learning because or more stable learning, which seems like it might be beneficial. But more importantly, doing it minimizing a distance to a common reference point means that even if there isn't total policy consensus, I see your question. Let me just finish this thought. Even if there isn't total policy consensus in the population, by minimizing a distance to a common reference point, we are more likely to be minimizing the divergence in policies in the population. Yeah, go ahead.
What is the distance, the type of distance you consider?
Let me go back and see if I can find.
Missed it.
It's this. It's you have, so it's the kind of the worst case distance for any given.
I suppose that P. Yes,
Oh,
but what I mean is like the norm one.
Yeah,
is,
yeah.
In fact, the P are distributions. So you consider the distance, which is the Wasserstein one, the norm, like it is one next to the norm, like this.
Yeah.
I think it's discrete action spaces, so
Yeah,
maybe
sorry, it is discrete action if that's what we're getting at.
So the one
Yes.
is like
So you
basically
mean
the sum.
Euclidean? Yes.
Yeah,
the
yeah,
Euclidean distance. Okay.
Yeah.
Okay.
Yeah.
Yeah. Okay.
That's all right. But as the reviewers on a recent paper pointed out to me, and that reviewer may well be listening now, of course, basing your metric on the similarity between the policies essentially does also give you bias, because it might be that a Q function that was estimated that seemed to give a more similar policy, but it was not actually a good estimation, ends up getting repeatedly prioritized over and over again. So that might not actually be desirable as a metric. So then I wanted to start thinking about better ways of choosing which policy to spread through the population. So again, we have these three terms, and it obviously makes sense that since we're trying to reduce exploitability, you might want to think instead about maximizing, choosing the new policy that maximizes the return, or the regularized return, in order to speed up convergence. The problem with that is twofold. One, it seemed to give empirically much less stable learning than going with the most similar policy, which is obvious when you think, again, we are that the Q estimation may be wrong. So choosing the policy that maximizes that potentially incorrectly estimated Q function is obviously going to give some unstable learning, even if it seems to get you there quicker. So I've got some, again, apologies, and this is why it's work in progress, some very messy, sorry, this is not the messy one, some reasonably messy plots, thinking about some of the different metrics we might use to choose which policy to spread. So what are the takeaways here? The takeaways here are that using the most similar policy is this green one. Or sorry, the key takeaway is that the independent learning algorithm still seems to perform better than both taking the most similar policy and the kind of the policy that maximizes these first two terms, the entropy and the maximizing the value, which suggests obviously not a benefit to the networked communication yet, even though intuitively you might think that there is a benefit to be gained. So this is the target coverage task. Then on the target selection task, this is the messy one. Probably too messy at this point to really get much out of this. It's interesting. So it's not super obvious what's going on in the exploitability, which is our main metric of interest, but it's kind of interesting that if we are maximizing those first two terms, which is the red line, you can see that it goes up a lot quicker. But then, as I say, it kind of seems a lot less stable than some of the other metrics, particularly this green one, which takes a bit longer, but then is a bit more stable. So I then thought, okay, so that neither of those ways of doing it seem amazing with respect to the independent case. So another way of choosing the just aware of time, I think we should be all right for time, because obviously we want questions as well. Another way of looking at, another way of calculating this metric to allow the policy propagation is, instead of maximizing one of these terms with respect to the estimated Q function, is why don't we, having updated our policies, we then evaluate that policy directly by kind of estimating for a certain number of finite steps the discounted regularized reward. The thinking being that might be less susceptible to, pardon me, some of that error. And also because the Q function that we're estimating, we're estimating it before the policy is updated, and hence also the distribution updated. So the kind of that Q function is, or that estimation is already out of date by the time we use it to choose which policy to spread. On the other hand, evaluating the policy directly is still going to be an estimation, because we're taking a finite number of samples rather than an infinite number. And also, if again, we're still going to suffer from the same problem of the distribution updates as the policy updates, but if we're then spreading policies through the population, that is also potentially going to change the distribution. So again, there's still a lag between the usefulness of the evaluation and having implemented it. So again, some not very helpful plots to have a think about what effect that might have. The key thing is that doing it this way, so now eval poll is what I've called evaluating the policy, is green. That now does seem to get us as good as the independent learning case. Obviously, still pretty tight, so I don't know that I've shown anything particularly convincing, but seems interesting. Obviously, I would like it to be better than the independent case, but at least we're now approaching it. Can't remember, right, again, a lot of mess here. What can we say here? We can say that interestingly, I guess the most interesting thing we can say here is that the reward increase in reward obviously doesn't always seem to reflect what's going on with the decrease in exploitability. I'm not going to try and draw further conclusions from these plots because clearly needs more runs and more to happen. Regardless of that, clearly still not that convincing that spreading the policy that way or kind of using communication in that way is of benefit. So then, and again, still aware of the time, so I'm going to try and get through these last few bits reasonably quickly. So far, as I said, I've pretty much assumed that we want to reach a single unique policy that gets spread through the population as we would have in the centralized case. The reasons for thinking about it like that is because, as I say, most existing work does use a centralized method, so it kind of just your mind heads in that direction that we would want consensus. And as I said, also having no policy divergence in the terms of the theoretical guarantees, that reduces the error in the Q function. So that seems like a reason to have a single policy. And also there's other reasons like interpretability. If everyone's following a single policy, that might make these, from a kind of a safety perspective, it might be good rather than each of 1,000 agents pursuing different policies. On the other hand, this is still a competitive game, even though they have symmetric rewards. So there's not actually any reason to have a symmetric Nash equilibrium, which is probably why the independent algorithms seem to be doing so well empirically, because they may have an incentive to deviate. And it seems that so far, all of the methods I've suggested for propagating the policy leads to some form of bias, be it biased because of the similarity of the policy to the previous one, or bias in terms of maximizing the reward and so on. So that might be affecting us. And as I say, if our primary goal is to reduce exploitability, it doesn't really matter if that comes from heterogeneous policies in the population or not. So if we kind of convince ourselves that we don't mind ending up with different policies, then another way of thinking about communication, rather than trying to reach complete consensus, might be the following. So now there's a brief diversion into something completely different that we haven't spoken about at all so far, which is distributed embodied evolution, which is a related but obviously quite different area. Some of you might be aware of. It's evolutionary algorithms are used, are kind of optimization algorithms that kind of think about evolving solutions to problems, particularly in terms of kind of parameters, by using mechanisms inspired by biological evolution. So there's this idea of parents, that there's a survival of the fittest, so the best parents are the most likely to spread their genes. There might be some crossover, there might be some mutation. And then distributed embodied evolution does that on an actual robot moving around in physical space, a bit like the games I've spoken about so far. And they can communicate their parameters to neighbors. And the idea is that evolution process happens by better solutions and more likely to be communicated to neighbors. And then that is then passed on to the next generation to improve the policies. Crucially, in this setting, there isn't an assumption that you want to find a unique policy for the whole population. And if anything, the opposite is true, that you want diversity because it helps to explore the solution space more efficiently. But it is similar to our setting anyway, in that there's an evaluation of the fitness of your current parameters that then gets communicated to allow neighbors to choose which one to adopt. So there's certain parallels, and again, hypothesis currently is that maybe drawing on this kind of area might allow communication in my setting to have an improvement over the independent case. So again, apologies for quite a lot of text on this slide. Key things here are the different ways that in the distributed embodied evolution setting, that agents choose which parameters to adopt are: one, you can just choose the one with the maximum fitness or minimum fitness if you times it by -1, which is basically what we've been doing, or what I've been doing so far in the existing work. But then we have all the problems that we've discussed so far with bias and error. Agents can accept policies communicated to them completely at random. So rather than choosing the maximizer or minimizer of the values received, they just take one of them. Obviously, that's not going to lead to consensus, but means that policies that come into contact, or agents that come into contact more with more neighbors, are more likely to spread, which for certain settings may be interesting. So if, for example, we're thinking about a game where the agents are meant to aggregate and cluster together, it's obviously good if parameters that lead to better clustering spread more through the population. So there's a kind of a feedback loop between the structure of the network and the way that the policies get spread. Or this final method combines the two, combines this idea of the policy evaluation with an amount of stochasticity. And there's various ways of doing that. It's almost like having a softmax. Rather than taking the maximum or the minimum value, you adopt a policy with a probability proportional to how good it is, rather than just taking the maximum one. So my hypothesis, which is very much remains to be studied, is that using one of these final methods might be beneficial, because we can still privilege better policies spreading through the population and also reduce policy divergence, which seems to be important for sample guarantees, while also avoiding some of the problems from unstable learning that come from incorrectly estimated Q functions or incorrectly evaluated policies, because we're more likely to take good ones, but we're not tied into taking any one. And also, as I say, if we're maintaining a somewhat of a diversity of policies in the population after the communication rounds, then there's going to be a less drastic change in the mean field, which means that those evaluations still apply more than they did previously. So there, again, intuition indicates that this might be helpful, but intuition also indicated that the other things that I've said so far might be helpful, and haven't yet got there. But this is the kind of direction I'm thinking of, and hoping that eventually I can find a way that communication can definitely be a benefit. Just one final slide, and then I'm happy to take questions of some other future work that I'll be doing, going back to your question from earlier about mean field games and non-stationary mean field games. Obviously very interesting as well, but a lot of the kind of the methods for solving non-stationary mean field games think about having the current distribution, the current empirical distribution, as part of the observation for the agent as well. Well, you can either do it, if it's indexed by time, you could have the time as part of the observation, or you can have the distribution as part of the observation. That obviously gives you a very big observation space. That's going to require moving beyond this quite simple tabular setting. But using function approximation and neural networks is kind of a non-trivial change to the algorithms as they currently stand, because you can't do that, the policy improvement step for each state in the same way. So there's some existing work, like the one mentioned here, that again, obviously some of you are aware of because your name's on it, which is going to help in that direction applied to this setting. And then if we're going to include the mean field as part of the observation space, it seems kind of unrealistic to think that you would only have a local observation of your state, but be able to see the whole mean field. So then we can also think about using communication for having a local estimate of the mean field and then communicating that and improving your estimate. So that is all remains to be seen how that all ties in. And luckily I've got 2 more years to worry about it. So apologies for not being able to show you anything more definitive that these ideas are good, but I'm hoping that in discussion with you and questions and further conversations, then we can find a way to bring this contribution really into light in mean field games. And as I say, very, very, very keen for interactions, suggestions, critiques, and so on. But thank you in the meantime.
Oh, thank you very much, Patrick.
Thank you.
Very interesting. So other questions or more questions from the audience? If you want, you can unmute yourself or raise your hand. Okay, yes, Panos.
Yeah, I'm the usual suspect, but
Hi.
if somebody wants to start before me, it's okay. I would like to ask first for the continuous case. Like you mentioned, this is on your project list. Do you have any ideas?
Yeah, this is not something I've given loads of thought to yet, and it sounds like you may have more ideas than I do about it. So far the thinking is, as in there's enough work to do on incorporating neural networks or kind of linear function approximation into this for purely just large discrete state and action spaces. Imagine that'll take a certain amount of time, and if I can then get to the continuous case, then even better. Is there a thought you specifically have about it?
No, just because I am doing something about continuous states and space. It's just I wanted to see like if you have any idea or something. But
no, I don't know loads about it, and I'd also be interested. Sorry.
It's okay. We can communicate at a later.
Yeah,
we can communicate at a later stage to exchange ideas or like for the continuous case. And
how
one
does
more question
how does the mean field get
go.
represented in the continuous setting?
It depends because I am not using neural networks or other things.
Right.
For the thing like I'm doing, I'm using kernels and I just do like the infinite dimensional setting using just distance between the measures to define the kernels. It's a very different technique. It's very particular as a technique for the moment. But if you are interested, for sure, we can discuss.
I think there'd be a certain amount of work to consider how to represent the empirical mean field distribution when in the continuous setting and so on. Because currently I've just got kind of bins that they all fall into, obviously.
Mm-hmm. And then my other question is about the communication part in your algorithm or in general. Like I suppose that you have some symmetry in the network that you put also.
Yeah, I mean,
in some sense.
Currently, it's an undirected communication network.
Yes.
But again, like so far, because a lot of the assumption is that any communication is better than nothing. So any reduction in policy divergence is better than nothing. I haven't placed any particularly strict assumptions about the network. So it may also be that in an undirected setting, then you would still have policy.
What I was going to ask is that if you add some cost to the communication, so it's like it's not you have cost to pass like from one vertex to the other or like traveling through the network. Then does this change the result or not? Like it's going to be the same since you make no assumption over it.
As in, would it be up to the agent to decide whether or not to take that cost, you mean? Or you mean it
Yes, if,
as in
if
like
like
a choice
communicating,
by the...
yeah,
Yeah,
yeah. So then,
sorry, go on.
then you will have a second optimization problem to
Yeah.
solve, in the sense of how you will pass the information on. So
Yeah.
if you want to, if your objective is all the agents to have the same information at the end, it's going to be different than just communicating the information through some path in the network.
Yeah. I mean, there's also an assumption so far that despite, as I've said, agents may have an incentive to deviate, I haven't, thought about kind of an adversarial setting where, I'm currently assuming that agents are incentivized to truthfully communicate their current policy, whereas actually you might have adversarial settings, or it doesn't even need to be adversarial necessarily, where if agents can do better by not truthfully communicating their policy, why would they do that? So that's also an area of work to think about.
Okay, nice. Other questions? So I think I have a few other questions, but I can maybe ask them later, or we can keep in touch. But yeah, one of them was related to this idea of optimizing over the communication, because it could be that the agents in real life, maybe there is not a prescribed rule that everyone is going to follow. So following your idea of, having a realistic setting, it could make sense that the agents decide to communicate or not, maybe with a cost or without a cost, but maybe they decide the rule according to which they are going to, communicate and adopt another policy or not.
There's work in that distributed embodied evolution setting whereby instead of the burden being on the receiving agent to decide which one to adopt, there's some work on the agent that on the communication side. It basically constructs the metric is not a concrete value based on the reward. It's what they estimate the value of their parameters to be relative to the others around them. And if they decide that it's good relative to the others above a certain threshold, then they communicate. So you can also have it on that side. There's another way of doing it where, rather than just broadcasting within their communication radius constantly, they might vary that radius depending on how good they think their own parameters are.
I see.
So again, there's like a lot of parallels in that area that might well be relevant to this, or might be interesting to explore.
All right, yeah. So if there are no further questions, well, thank you again very much, Patrick, for the nice talk.
Pleasure. Thank you very much. If anyone has any questions or comments afterwards, as I say, genuinely more than happy to continue the conversation.
Okay, great. Thank you.